Okay, this is number 11 in your exercises, and you'll be asked to do number 12 and 14. So I'll go ahead and do 11 and 13. So we'll start with number 11, and it states use a method of example 4 to find two linearly independent power series solutions of the given differential equation. Then determine the radius of convergence for each series, right? And then, of course, identify the general solution in terms of our familiar elementary functions that we've been working with I think on page 195. And I did ask you to, I believe, ask you to read example 4 in your book. Was it example 4? Yes, it's a very important example. And again, I think the author does a great job explaining it. Okay, so let's start 11. So we want to assume that there is a power series representation here. And we have, whoops, well, that's a nice blue, but I won't use this blue yet. Okay, so assume that Y is this power series representation, right, this infinite power series. Okay, well, this is a second order differential equation, so I'm going to have to find the second derivative. So then, okay, y prime, we've been finding y prime, so this is just going to be n cn x to the n minus 1, right? And again, we're starting at 1. But now we need y double prime. So again, using the power rule, I have n times, and I'm going to bring, right, this guy down here. And so I get n minus 1 cn x to the n minus 2, right, because I'm subtracting 1. And again, here I'm going to start at 2 because when I plug in 2, right, then I start at, if I plug in 1, I'm going to get a negative 1, so I have to start at 2. Okay, so that's, again, this is the basic idea. So now let's, let's back. So abbreviate here, substitute y, and actually we're only going to need y double prime back into our differential equation, right? Because there's no y prime, this is really y prime prime. So I'm actually going to rewrite this. We can write this, right? We can just subtract y, because we want to use identity principle eventually. So I know I'm going to set it equal to 0. So let me just write that down. So y double prime minus y equals 0. So let's back substitute. So y double prime is right here. So y double prime is, so this following summand, n minus 1, cn x to the n minus 2 minus y, and again, my y is my original choice, which was summation, and it was just cn x to the n, and of course we start at 0, and then that's all equal to 0. Okay, so I have my a couple of power series here, and again, in order to, the goal is to find this a recurrence relation that will help us, explore a pattern to find our CNs. But we want to make sure that our powers, right, match, right, x to 1 power, x to 1 power. Usually you want to stick with the n. So we can use a dummy variable here. And I think I chose green last time. So I'm going to call that k. So again, I'm using, right, dummy variable. So I'm going to let k be n minus 2. So if k is n minus 2, then if I solve for n, right, I just get k plus 2. So this is that part. And let's go ahead and rewrite this. So n is k plus 2. So when I see an n, right, I'm going to replace k plus 2. And then here, right, this is n, so that's k plus 2 minus 1. Right, so I'm really putting in a k plus 2 there minus 1, which is just really k plus 1. Cn, or ck plus 2, times x2 rk. And then I'm just going to rewrite The next command. Okay, so I'm using again a dummy variable, a placeholder variable. So now, right, I have x2, right, one term, x to one term. Oh, and actually I forgot to change my, well, my indices is k. So I started with 2, right, with n equals 2. Well, if you substitute 2 here, 2 minus 2 is 0, so you know you have to start at 0 to infinity. And again, right, if you still are doubting that this series is the same thing as this series, you know, feel free to plug it in. Expand this series, expand this series, and you'll see that you have, I mean, it's going to be the same term by term. Okay, so indices, well, indices actually look great, right? This is, I mean, 0 and this is 0. Again, k is a placeholder variable, so now I'm going to go back and replace all my k's to n's. Again, why n? Because I have n here. I mean, if we're using p, then change it to p, but we're calling it cn's. So every k is going to be n. So n is 0. Okay, k plus 2, n plus 2, k plus 1, n plus 1, c n plus 2, x to the n, and again, rewriting this guy. And again, make sure you write every power series down. Skipping steps only causes errors, so again, I encourage you to write every single step. Okay, so we can use power series operations. So I'm starting at n equals 0 to infinity, and right, I'm basically factoring out a x to the n. Let me just get a different color here. We have, right, I'm really factoring this guy. So I have n plus 2, n plus 1, cn plus 2 minus cn. Right, my x to the n equals 0, right? That's just using power series operations, right, term by term. And, well, now we can use the identity principle, right? So maybe by identity principle, right? Basically here we are going to equate our coefficients, right? Our infinite coefficients, infinite sum of coefficients. So we have n plus 2, n plus 1, cn plus 2 minus cn equals 0. Again, if you're having trouble, you know, seeing these terms, I mean, again, this is an infinite sum. If you want to write a couple of terms out, I mean, that's very helpful, especially if you don't feel as comfortable with power series. You know, write out the terms. I mean, obviously you won't write, you don't want to write infinitely many. It's impossible. That's why we have this nice shorthand notation. Okay, so if we continue, right, this is just going to be, we'll write this out, cn plus 2, and I'm just going to bring my cn over, and my goal is to solve for cn plus 2, and this looks very nice, n plus 2, n plus 1, and then I have, there is my recurrence relation. So recurrence relation. And I'm going to stop here because, again, it's going to be a little bit, there's more work here. We'll explore the pattern in the next video. And yeah, I'll continue the videos. I have not forgot about your test or your homework. It's been a very busy week, but it will be done today. In the evening, but it will be done today. Okay,